So, I'm going to talk about curvature film limits of the chiral Dirichlet energy, and I'm going to explain you why we call chiral this kind of energy. I want to say that this is a joint work with classical. And a quick thing, so this number that you see here will not be the page number, but will be the number of elements that you will see on the slide, so don't be worried if it increments too much. Okay? So what we want to do is we want to investigate the curvature film limit of this kind of energy, which is a classical energy, but in which there is this kind of perturbation that depends on this vector field B, which is a Sobolev map between a tubular neighborhood of an epsilon tubular neighborhood of an n-1 dimensional submanifold n over n, and which take value in an m-1 dimensional submanifold of Rn. So this is the kind of energies that we are going to investigate, and I'm going, of course, to motivate why we are interested in this kind of on the thin film limit of this kind of energies. So the perturbation here that you see is essentially a function defined on the target manifold M, which at every point of the target manifold associate a linear operator. You can think this as represented by matrix. And of course we have to do some hypotheses on the regularity of this K in order to get what we want. Okay. So let me give you a preview of the result, which is meaningless at this stage because it's really vague, but nevertheless, let's take a look. So we consider this family of energy, which is here by one of the epsilon, and we say that this we are going to show that this kind of energy, this family of energies, gamma converge to an energy function which is defined on the manifold N, whose shape strongly depends both on the curvature of N and of M, and depends on the curvature of N and M, but just in the through the normals. To the normals of to N and M. And the result that we get has some implication to relevant systems like magnetic materials. So I have to say that the specific form of this energy function, which is the case in which N, so the surface that generates the tubular neighborhood is planar, M is S2, and K is an antisymmetric matrix of the form dot cross V, so it's the matrix which acts like a cross product. This has been recently addressed with Michele and Dirk, me and Elisa Davoli in the framework of macromagnetics, because it's what will give you what is called the bulk DMI contribution. In fact, yes, with this specific choice of K, of N, and of M, you will get exactly the model for Zariski-Mourier interaction. So the macromagnetic model, which accounts for Zariski-Mourier interaction that you learned a lot yesterday, I think. And which are the primary mechanisms behind the emergence of this chiral spin texture known as magnetic skyrmions. So even in this particular case, so when N is a planar surface, M is S2, so we are in the classical setting of macromagnetics. Well, there was an interesting new physics that came out because some part of this bulk DMI energy will contribute like an anisotropic term. So already in this really specific setting, something new were coming out. Well, our extension still envies some new mechanism behind, because we observe that when M is no more S2 valued, but is even a small perturbation of S2, so the target manifold is no more S2, then in the thin film limit you still have to add a new contribution, which depends both on the curvature of the target manifold and the curvature of the base manifold. Okay. Yes, also, as I was was saying, so when we consider this general framework, we get this anisotropic term, which both depends on the curvature of the infinity and the curvature of the Dirichlet manifold. And given the role and importance of this energy in the context of antisymmetric exchange interaction, we decide to call this kind of perturbed Dirichlet energy chiral Dirichlet energies. Even when K is not antisymmetric, okay? So we stick with this name no matter if we choose for every V an antisymmetric matrix or a symmetric matrix or a generic matrix. Okay, but up to now everything is ultra vague, so in the next slide we are going to explain all these highlighted words, so what we mean by curvature regime, what we mean by antisymmetric exchange interaction, how we model this, and what is the result that we get in the limit. Okay, let me take into account the simplest scenario, so the simplest possible scenario from mathematics. We consider just the so-called exchange energy, which is kind of elastic interaction, plus the, well, I write here also the magnetostatic energy, but it will not play any role in what we are going to say. So in simple crystal ferromagnets, the observable state of magnetization are essentially the local minimizer of this energy functional. And these are configurations which are in H1 omega S2. So omega is the region occupied by your ferromagnetic body, M is the magnetization which is S2 valued. And the configuration that you are going to see, the observable state of magnetization, are the minimizer of this energy functional here. Where, okay, this term here, I start with this term which is a non-local term, and you will see that it's defined on all R3 here, while the exchange energy is just defined on the omega. So this term is nothing but the potential, the magnetostatic potential, which is the solution of this Poisson equation in the whole space. So minus Laplace nu equal to divergence of m chi omega. Well, there are parentheses here. This is the divergence applied to m chi omega, which means the extension by 0 of m to the whole space. Okay, so this is the no-local term that you still learned a lot yesterday about. And we are, well, what is more important to us is to understand where this term comes from. So this term always appears when you have a kind of, you model some continuum mechanics, yes, some continuous theory with assuming that there is a kind of elastic interaction between the constituents. So in fact, if you remember the Heisenberg, the typical Heisenberg expression of the symmetric exchange interaction, so you have a sum, a double sum or possible couple of spin attached to the lattice point of the lattice. Then the continuum equivalent, so if you change a measure, you go from a discrete measure to a continuous measure, what you will get is exactly this kind of energy here, this kind of interaction. So on the continuous level, you can assume that your exchange interaction has this kind of shape, which depends on the dot product between m of x and m of y. Here you have a double integral. And omega epsilon is kind of a kernel which weights the interaction between two magnets, two spins, which are distant modulus y minus x apart. Now, as you can see from here, this is really a symmetric exchange and symmetric energy, meaning that no matter if I have a spin, okay, these two spins that you see in this figure here, they have exactly the same angle. As soon as you attach these two vectors at the origin, these have the same angle. And so this will have the same exchange energy. But in recent time, they observed that this kind of configuration actually contributes differently. And most of these phenomena related to magnetic skyrmions are explained as soon as you introduce some new other term which takes into account the difference between this type of configuration and this type of configuration, okay? Which are not discerned by this kind of energy. Now, what is the link between this energy and this exchange here? Well, you have to remember the Bourgain-Brezis-Mironescu formula. You observe that this is a S2 valued vector field. So this dot product which is here is nothing but up to something which is relevant from the variational point of view is mx minus my all to the square. And so you know that as soon as you take this family of a kernel which concentrate around the origin, then under appropriate hypothesis, this term for epsilon goes to 0 really converges to the gradient of m squared. Or if you don't want to use mathematics but just a little bit of intuition, just do a first order expansion of this. Forget about omega, go to all R3, do a first order expansion of these terms, and you will get exactly this gradient m squared. This is the approach, for example, that is in the Brown book on magnetic. Okay, so as I was saying, however, magnetic materials with low crystallographic symmetry can exhibit weak antisymmetric exchange interaction, usually referred to as the Jaruzelski-Moria interaction. Let's see how we can model this kind of antisymmetric interaction. So, if you go, for example, just on Wikipedia, take Jaruzelski-Moria interaction, antisymmetric exchange interaction, you will find that this kind of energy is a double sum over all possible lattice points of an energy like this, in which this is a vector which does multiply the cross product between the magnetization at the lattice point x and the magnetization at the lattice point y. Well, the natural extension to the L2 setting is to consider this kind of double non-local energy here. And here you are forced to, not the here well, before the energy, the kernel here was depending on the distance between y and x. Now you really have to take into account the relative distance between y and x, otherwise this will be 0, this integral. If you put the modules here inside, this will be 0. And you will see immediately that in order, by just switching the role of x and y, the epsilon vector must satisfy this kind of relation. Okay? Usually this vector here, the epsilon really has some physical meaning depending on the lattice structure. And there is this paper from 60s from Moria which tells you how you have to choose this vector, the epsilon, depending on the symmetry group of the lattice that you are considering. Okay, still works? Yes. Okay. Now, well, under appropriate assumption, this is the epsilon, you can do an argument similar to the BBM formula and get that this energy in the limit, as soon as this vector concentrated around the origin, will converge to an expression like this. Okay? So, in the very short range limit, so when you consider just interaction which occur between spin, which are not so far apart from each other, then the limit that you get is this kind of expression here. Where these di are nothing but constant vectors, okay? Whose shape depends on the symmetry of the crystal lattice. And in fact, if you see this energy here, this is the more general type of Jaruzelski-Moria interaction that you can add that to the exchange symmetric interaction in order to explain this emergence of Magnitsky. Okay, let me. Yeah. So overall, if you consider both symmetric and antisymmetric exchange energy, the energy function that you have to investigate is the following one. Right? It's just the sum of the two contributions that we explained before. But now we can do some algebra on this expression and to rewrite it in a more convenient form for us. So how we do this? Well, you introduce this J linear operator which maps the standard basis over 3 to these vectors di, which are the Jaruzelski vector, which are fixed a priori. This really depends on the lattice that you, the crystal structure of the material that you are considering. You introduce this matrix M, you do some really simple algebra, and then you get that this expression here can always be written in this form, okay, where this K is a matrix. What's matter for us is just that this K is a matrix, nothing more, okay? So that is a matrix valued function, meaning that for every point on the S2, because M is S2 valued, for every point on S2, you have a matrix K associated, a linear operator K. And when I write this norm here, I mean really the norm of a matrix, so the square norm of all the entries of the matrices. Okay? So we get this term, which is what we are interested in, plus this term, which is really trivial to treat from the variational point of view as soon as we are interested in the gamma limit. So we will focus really. That explains why we are working on this kind of energies. Yeah. So from now on, I will not take into account this term, and just explain why we are interested in this perturbed Dirichlet energy. We not focus also on the magnetostatic self-energy because this has been already treated. First of all, we are really working from n-1 dimensional submanifold to n-1 dimensional submanifold, and so in this general dimension does not make any sense to talk about the field operator. And then if we are in the classical setting, which we are in R3, well, then the passage from R3 to compact surface has already been done, and the methods here then can be used for also to attach this other contribution to the energy that we are considering. So we really just focus on this term here. Yeah, overall it is sufficient to study the energy H omega to comprehend how the MI affect magnetization behavior in curvature layers. Okay, let's talk about the main result. Well, let me tell you this. The result is interesting from my point of view. The mathematics more or less is the same that we already use in some other paper, so it's not so big a deal, I would say. Okay, but the result that we get is well, we hope at least that there was some kind of new physics inside, although we cannot still justify this even if we do the physics. But we found a nice paper we will see later that at least justify why one can be interested in this kind of results. So we consider, as said before, n and m, which are closed and smooth C2 hypersurface of Rn and Rm. For every epsilon between 0 and some delta, we consider the tubular neighborhood omega epsilon. Delta is just the maximum tubular neighborhood that you can build around your process surface. And for every v, we consider this energy function that I wrote before. So is defined on this tubular neighborhood of the base manifold. And we are interested in the asymptotic behavior of this family of minimizer when epsilon goes to 0. That's classical thing to investigate. Well, in order to do this, I have to introduce some notation, unfortunately. So, which is a kind of pullback of this energy on the base manifold via this map that is written here, which is the map which make the tubular neighborhood into a cylinder. So maps a cylinder, a curved cylinder into this tubular neighborhood. So using this map, we can write this energy functional under this form, in which this tau I are mainly in each point of the target manifold we consider an orthonormal basis. So an orthonormal basis which consists of the basis of the tangent space plus the normal. And then we project our gradient on this basis. And this allows us to write this expression that is written here, and with this square root of G epsilon is the classic metric factor. And that can be expressed in terms of the principal curvature of the surface. Well, these guys here are the one that relate the gradient with respect to the Cartesian coordinates to the gradient with respect to this basis that we choose. Okay, now I reported here again the two energies just to let you read the theorem, having in mind what are the meaning of G epsilon and of this E epsilon n. And what we prove is a classical gamma convergence result that for every epsilon, the minimization of this family of energy functional is equivalent to the minimization of this family of energy function. Equivalent in the sense that if V epsilon is a configuration of this energy function which minimizes the energy function, and then just by composing this minimizer with this function of psi that we saw before, we get a minimizer of this E epsilon, and vice versa. So you can pass from one minimizer to the other just by change of coordinates. Well, this family of minimizers is recursive in the wake topology of H1, and the gamma limit has this expression. So is I'd say is an integral on the base manifold n of the classical gradient, tangential gradient, plus this contribution which is projected on the tangent space, and then we have this term which we will see later. That's the interesting part. Always disappear when m is S2. So when m is S2, at least in all in all the physical application one is interested in, when m is S2, this guy always disappears. So in macromagnetics, in the pure theory of macromagnetics, you will not see this term that appears here. But as soon as for some reason your magnetization is not precisely S2 valued, and we found some reference in which really you can have a kind of saturation magnetization, which is the intensity of the magnetization, which depends on the direction of m. So maybe some material in which if the magnetization is along an axis, then has some intensity. If it's not another axis, has another intensity. Then, for example, m is constrained now to be no more S2 valued, but valued on an ellipse, okay, an ellipsoid. And then in the 2D limit, then you really have to take into account also this new term, which depends on the normal to the base manifold and to the normal to the target manifold here. Okay, and since we were also investigating some more general framework, we were also interested in the case in which this K here can depend really on the points, okay, on the points on the base manifold, and you have also metrics that multiply the gradient here. So for some kind of Zalewski-Moria type interaction we are interested in, you really have to consider this more general setting, and then you have to do some hypotheses on this perturbation K and this matrix A in order to achieve that you have this generalization of the previous result, in which now there is the new contribution as this shape. Okay, this is more or less what we got before, and now this is plays a contribution also here. I don't pretend that you will recall this expression after one slide, so I will be. It's not even important for what I'm going to say later, because from now on we are going to see specific application of this general result to macromagnetics. Okay. If time is okay, yes. Okay. So let's see the application to macromagnetics of this result. A lot of people have talked about magnetic skyrmions. In the last years, we are really interested in magnetic skyrmions, not really just because there is this Zalewski-Moria interaction which explains magnetic skyrmions in planar thin film, but maybe the presence of this magnetic skyrmia due to the geometry of the base manifold, so that you have a closed surface, and this allows you to talk about topological degree and so about topological protected states. And so the rest of the talk shows how this curved thin film limit that we found account for various situations that matter as when ferromagnetic crystal lack inversion symmetry, and so that Zalewski-Moria interaction can reach the otherwise uniform ferromagnetic state. So the crucial point is that due to material defects or anisotropy in saturation magnetization, maybe I just have to, when I say anisotropy in saturation magnetization, maybe I can just, is that true? Yes. just it's missing a small thing that I have to write. That usually you have in macromagnetics, you have the magnetization M, which is of the form MS, which is the saturation magnetization, and a unit vector M. Okay, you can always write magnetization macromagnetics in this form, which this is a constant, which maybe depends on the temperature, and so on the point of the base of the domain if the temperature is not uniform in the domain, but this is the expression. So in the usual general case you have ms of x, m of x, with this in S2. That's what you get usually. But now it seems that there are some situations in which this ms can depend, other than x, also on m itself. So it means that this m here is no more on S2, but depending on the direction of m, you can be, for example, on an ellipse. Okay? So this is the framework which is also included in our analysis, and in some Nature paper that we found, they say that discovered this kind of material, which if the magnetization is out of plane has some saturation magnetization, if it's in plane has another saturation magnetization. So a specific instance of our findings provides a model for curvature fields in the presence of bulk DMI, in the presence of the interfacial DMI, and for completeness we also treated the case in which the temperature of the ferromagnet is not uniform, which is the case in which this ms just depends on x. But our scenario, our analysis also treated the case in which ms depends also on m. Well, let's see, isotropic bulk DMI. Isotropic bulk DMI arises when this Jaruzelski vector, and just a remark here, although it's quite small, I wanted to report which are the expression of H omega and HDM so that you can do your substitution. So the isotropic bulk DMI occurs when this Jaruzelski vector, di, which are here, are the standard basis over 3. That's the case when you get the classical bulk DMI. Well, maybe some of you is familiar with the classical bulk DMI in the form of Karl m dot m, but this is exactly the same expression. Up to a constant term, you will get exactly the same expression. This guy, when di is the standard basis, will give you Karl m. Okay? Just remember that Karl of m is equal to ei crossdim, sum from e, that goes from 1 to 3. Okay? So in this, if I write this expression in our framework, this forces us to choose this k of the form k dot cross m. Okay, what I mean by this expression is that for every m, you have to associate to this m the matrix, which to every vector associate k that vector cross m. And in this case, which is the expression of the G epsilon we are interested in this case, is just the one that is a perturbed Dirichlet energy, in which this guy that is here is the so-called helical derivatives. That's the name used by Melker, for example, in this first paper on this magnetic skyrmion. And if you apply our analysis to this kind of perturbation, in the limit you will get this expression of the energy function. So this will be the expression that you get when you consider two-dimensional surface in R3, M and N, where N is the big manifold, N is the target manifold. And in particular, if N is a planar surface, you get that this guy is E3. And here, now, if M is S2 value, so if we are in the setting of macromagnetics, this term disappears. Okay, so I really want to stress that this is the term that you get in macromagnetics. And as soon as the magnetization is not precisely S2 value, then you have to consider also this other contribution. Yeah, okay, this term is always disappear when, no matter if n is a planar surface or a closed surface. Okay? The important thing is that the vector field you are considering is S2 valued. Every time the vector field you are considering is S2 valued, well, what is the normal to S2 is just M. The normal to S2 in the point M is just M, because M is immediately vanish. Okay? But if not, then you have to consider this kind of contribution. Well, let's talk about isotropic interfacial DMI. What is interfacial DMI? Well, is the case in which the Zalewski vector, so that vector here, di, have this expression, where tau I recall you is the basis of the tangent space. So that's the expression that this di must have when you consider interfacial DMI. Interfacial DMI occurs when you have an interface that separates two different materials, and so these two different materials, which has different crystal structure, create this lack of symmetry in the whole structure of the crystal. So if we rearrange in our framework in which we have this perturbed K, then the expression of K is the following one. As usual, what does it mean, this expression? It means that to every M, you associate the matrix, which to every vector associate the value of this expression when in the dot you put the vector. And note that K now depends also on psi, where psi is the projection on the point X of omega epsilon onto the base manifold. And therefore, to treat this case, we really have to use our generalized version of the theorem. But nevertheless, at the end, what you get is, again, that in the limit, you get this expression here. This term is quite classical, plus the term that you see here. And again, if you are in the classical setting of macromagnetics, so if M is S2 valued, then this guy vanishes. But if not, you have to consider this small contribution here. And this is really the expression that, I mean, if you expand this norm, you really will get the classical term divergence of M perp multiplied by M parallel minus grad M parallel dot M perp. So this is really what you get in the usual term that you get when you treat interfacial DMI. Okay, I think that I'm almost done, so we can have a coffee break before schedule. Okay. So the last thing that I want to say is about the non-uniform temperature setting. So, okay, this is the setting, as I told you, in which this MS depends, since this translation magnetization depends on the temperature. If the temperature is not uniform inside the material but depends on the point X, then also MS will depend on X. And here, in fact, but this is strange enough. This is the last version of the slides. Good. So I sent you the previous version, in which there is a reminder instead of a reminder. So this saturation magnetization is was explained before, is a temperature dependent material constant, which vanishes above the so-called temperature. And mean field theory predicts that the value of this MS can be considered almost constant in the ferromagnet when T is really below this Curie temperature. As a result, as I was telling you before, is customary to express the magnetization under the form MS-M, where M is S2 value. And it's what also we did when I was introducing this H omega here. I was assuming that M was S2 valued. But now, if this, since MS is temperature dependent, if this temperature is not uniform in the ferromagnets, then we have to consider the more general case of this energy functional, in which there is MS of X here and MS of X here. And this can be treated with the generalized version of our theorem, which I recall you is the one in which we have an AX here and x here. Simply by setting A equal to MSI and Kx equal to this matrix here, we are assuming that this variation in the temperature is smooth. Okay? And we just need to apply the second result that I showed you with this A and this K. And if you prefer in matrix form, this K has this expression that you can see here. And we are treating the case in which D1, D2, and D3 are really in general position. Okay, the limit that you get is the following one. And again, the expression is not so important. What is important is that you get again this blue term that vanishes when m is less to valued. So again, even in the when you have variation in temperature, but you are in the classical macromagnetic setting, assuming that m is less to valued, you don't have any additional contribution. But as soon as, from some reason, you have an isotopy in the saturation magnetization, or for some reason m is not constrained to S2 but to a bloody general target manifold, then some new physics can occur. Okay, that was the message that I want to send. And here, just if you want to know more about this, there is this archive with recently with the Valeri, and also you can find something in my previous work with Kirill, Michele, Davolin, and so on. And here you will find a lot of other references which are really interesting. Okay, but the entry point can be this for you if you are interested in what I said so far. Okay, thank you for your attention.